we're going to do an example of calculating what percent is unprecipitated. And this can be done in a precipitation question or a fractional precipitation problem. So kind of either way you can see a question like this. We're going to figure out the percent of silver that's unprecipitated when you add potassium chromate and silver nitrate. Okay? So let's get going on this question. This question is actually, at least this quarter, is in your homework. And it's in your textbooks, number 35. To get this started, because we're mixing two things together, the potassium chromate and the silver chromate, they're going to change concentrations once they mix. So we need the concentration upon mixing. So we're going to calculate the initial concentrations. This is pretty normal whenever you mix two things. And you often see in this chapter, when you're mixing you're going to mix two things and you're going to have to use the dilution formula. So M1V1 equals M2V2. Or to write this another way, M2, the final concentration, which is what I want, is M1V1 over V2. Okay, and that'll help me calculate my final molarity. Alright, so let's do that for this example now. For the chromate concentration, CrO4 2 minus, that concentration is its M1, initial molarity, 0.350 molar, times its V1, initial volume is 200, and the final volume is 200 plus 200. I'm adding, both of them are 200 each. So it's going to half this, I think that's 0.175, 0.175 molar. Now let's try it for the other one. For the other one, the silver nitrate, we've got Ag plus is what I'm finding. Its final concentration will be its M1 initial concentration, 0.0100 molar, times 200 milliliters. It starts off initially. In the end, the final volume will be 400. So it's just going to half that number as well. So that'll be 0.05 molar. Well, that's a crazy one. Okay. I don't need all those zeros. There we go, that's that one. Let me get some different pens out. So those are the initial concentrations. Let me label them a little bit better too. Just so we know, just so we remember. I'm going to put a little 0 on the bottom of both of those just to remind me they are initial concentrations. Okay, now what do I want to do? There's a couple things I can do. What we're expecting, I'll write it over here on the right hand side. We're expecting that the silver and the chromate will form this solid according to this reaction. So according to that reaction, really the reverse reaction, when you add the two aqueous, the silver aqueous, silver nitrate, and the chromate aqueous, that's potassium chromate, that it'll go the reverse direction and form the silver chromate. And because we're working with insoluble things, the silver chromate solid, that will be the favored side. KSP we're expecting is small. You do need to look that up either in the textbook or online. That's 1.1 times 10 to the minus 12. So you can see the reactants are very favored. Okay, now we want to calculate how much of this is unprecipitated, meaning how much silver is left over that doesn't become silver solid. Well, so we're expecting a precipitate, but we can double check if you want. You actually don't have to, but you can calculate Q according to that reaction is silver plus, and there actually should be two silvers here, because the silver is plus 1, so you should have two silvers in your reaction. So it's silver 1 initial squared times chromate initial. So there's the Q equation. We're going to plug in the numbers I just found to see, hopefully, Q will be larger than K, shifting this to the left, meaning there will be a precipitate. Let's just double check that. 0.0050 squared times 0.175. Okay, so I just plugged in both numbers, what I just calculated up above. And this turns out to be 4.4 times 10 to the minus 6. Which you can see is greater than KSP. So because 4.4 times 10 to the minus 6 is greater than KSP, we're going to have a shift to the left, and that means yes, we will have a precipitate. So that's good to find out first, just to make sure something's going to precipitate. Now, let's go on to the crux of the calculation. To get there, what's actually most helpful if I write the reaction out again. So let's write the reaction out again. I'll write over here. Silver chromate solid goes to silver plus, there's two of them, plus the chromate. Okay, because I want to find out how much precipitated, it'd be helpful right now to do an ice table to find out how much is actually used up. And so that's what I would like to do, but you're going to see there's a problem here right away. So if I try to set up an ice table, this number is 0.0050, this number is 0.175. Those are both the initial concentrations. And you should be, right now my question to you is, can I proceed? And actually you can't start your ice table yet. And let me show you why. Because, first of all, I would ask what's the favored side. You should say this side, because K is really small. If that's the favored side, remember from the last chapter, I need a 0 on the unfavored side. Or in other words, this reaction is going to go to the left because K is so small. So, I need to do that. I need to subtract off 0.0050, the smaller number, from both sides. However, there's another little sneaky trick in this one. I need to subtract off 0.0050 times 1/2 for the chromate. I don't know if you see why, but see how there's two silvers? Since there's two silvers and there's only one chromate, I have to subtract half the amount of chromates. Usually, yeah, I don't think we've totally seen this at this point, but something like this is going to become more apparent. So because there's twice as many silvers as chromates, I need twice as many as these. So here, this is going to be 0. This is going to be 1725, I guess. 5. And now this becomes the I line in my ice table. So that's the I line now. Now I can go through my ice table and figure out, okay, how much silver am I actually generating, so I can go through my calculation. So now, ignore the solids C and E. Okay, so I'm starting my ice table now. Again, I have the I line. It has to shift towards the right, plus 2x and plus x. Okay, so you should have something like this right now. Okay, and now let me set up my K expression. Okay, so KSP is products times reactants, or silver, 2x squared times 0.1725 plus x. Okay, and that's what I have right now. Let me review one thing here before we go on. See this 2 right here? We actually have that 2 appear in a potential, and it reached that potential here, of 3 places. Let me show you the 3 places where that 2 shows up. right here in your K expression, that squared. That's one place it has to show up by definition of what's called the law of mass action or the equilibrium expression. Place 2, the C line, right here, has to show up here because of the molar ratios. In place number 3, I didn't use this word yet, but this is the stoichiometric part of the problem. In the stoichiometric part of the problem, that's the third place it shows up. Actually, here, or really this is double, 2 times this one. So those are the 3 places you'll see coefficients that are not 1 show up when you're doing this kind of problem. Okay, KSP we already know. It's 1.1 times 10 to the minus 12. So we can solve for x, basically saying that this x right here is really tiny, smaller than that number. And you can just do the math to solve for that x. Let me write that final answer down. X is going to turn out to be, and you won't need the quadratic, 1.3 times 10 to the minus 6. So x will equal 1.3 times 10 to the minus 6 molar. And that would be the double, well, you have x, 2x is what we're interested in because 2x is equal to the silver concentration. So 2x equals the silver 1 concentration. And so what's that? 2.6 times 10 to the minus 6 molar. Okay, so that's how much silver there is at equilibrium. Okay, now I want to find one more step, the percent unprecipitated. So percent of silver unprecipitated. How do you go there? Okay, how do you do this last step? Well, to find the percent unprecipitated, that'd be 100% times what we're going to put on top is the amount of silver at equilibrium. That's the amount that didn't precipitate, didn't become a solid. It's still a liquid, 2x, or aqueous. And we're going to divide that by how much we started with. Okay? So the amount we have right now is 2.6 times 10 to the minus 6. Okay? Now, how much did I start with initially? That's way back when 0.0050. And this turns out to be actually a pretty small number. 0.0, let's see, 52%. Okay, why is this a small number? Well, let's think about it. If this reaction favors the left-hand side, we'd expect all the silver and chromate to pretty much disappear and become all silver chromate. So we'd expect near 0 amount of silver left, and that's why we find near 0% of silver. The smaller KSP is, the smaller this value would be. Smaller KSP would be, meaning it shifts to the left, precipitates, and that means there'd just be less aqueous left over. Okay? So that's how you do one of these precipitation problems.